Hi everyone, welcome back to Kitchen Science with Hollie for Becker School Supplies. So today we're gonna get wild with water. I'm so excited. We're gonna read a great story all about the wonders of water. But grown-ups, after the story, we're going to need warm water and cold water. So right now, make sure you're gonna have warm water and keep it warm till after the story and add some ice to your cold water so it's nice and chilled for our first experiment. Okay? Let's get started with our story. So let's look at the cover. What do we think this story might be about just by looking at the cover? You may have seen the frogs and the lily pads. It looks like they're in a pond. So what do you think the story might be about? Could be about frogs or ponds. Now, the title is Water Can Be by Laura Purdy Salas, illustrations by Violetta de Bija. Water can be what? What do you think water can be? I guess that's what the story's about. So let's read Water Can Be. Water is water. It's puddle, pond, sea. When springtime comes splashing, the water flows free. Oh, I love that word, splashing. It's a great way to describe how water moves around, huh? Water can be a tadpole hatcher, picture catcher. How is water a tadpole hatcher? Well, that's where frogs lay their eggs. And when their eggs hatch, what comes out of them? Tadpoles. So the water really is a tadpole hatcher. And what's the little girl doing on the other page? Yeah, it looks like she's splashing in puddles. And she's looking into a puddle, and what does she see? She sees herself. She sees a reflection. So water can sometimes act like a mirror. Water can be an otter feeder or a downhill speeder. Wow, that water is moving fast. Water can be a garden soaker or a valley cloaker. Why do you think the page looks all blurry on the side where it says valley cloaker? Because it's misty or foggy. Water makes up mist and fog, and that's why that picture looks all sort of blurry. Water could be a thirst quencher or a kid drencher. I love these two pages. They both give you different feelings when you look at them. Now let's look at the page with the kids on it. What are they doing? Yeah, they're running through the sprinkler. Oh, and it's so loud and bright and happy. Now, is our page with the deer loud and bright and happy? No, it's quiet and still and calm. The illustrator of this book was able to make us feel excited and loud and happy with our one page and calm with the other page. So cool. Water can be a drink cooler or a rainbow jeweler. Have you ever seen a rainbow? Yes, you can't have rainbows without water. The reason we can see rainbows in the sky is that the water breaks up the light into all its different colors, and that's how we get a rainbow. Water can be a homemaker or a ship breaker. Ooh, these are two other pages where you get a very different feeling from them. How do you think the page with the homemaker or the jellyfish on it feels? Is it a different feeling than you get looking at the page that says shipbreaker? Yes, the page with the storm on it has a very different feeling than the page with the jellyfish on it. Very cool. Water is water. It's fog, frost, and sea. When autumn comes chasing, water can be a cloud fluffer or a fire snuffer. School drinker, bruise shrinker. Let's look at the page. What do we think happened on the page that says bruise shrinker? Yeah, it looks like maybe the kid fell down and hurt their knees. And I see a bag full of something. Why are there cubes or squares in that bag? Right, that's the water. It's been frozen into ice cubes. And it's the ice they're putting on his knees. Have you ever fallen down and needed an ice pack? Yep, it helps to make us feel a little bit better. Water can be a salmon highway or an eagle flyway. Now, I got a special task for you. When we're all done with the webinar, look up videos on the internet of a salmon swimming upstream in a salmon highway. It's so cool. And this picture is really neat, but you should see it in video in person. Water can be a storm creator or a decorator. How is water a decorator on this page? Yes, water has made ice on the window. It looks like it's a nice frosty day, and there's ice crystals on the window, and they're beautiful like a decoration. Water can be a woodchuck warmer or a snowman former. I love making snowmen. Water is water. It's ice, snow, and sea. Now go and discover what else it can be. Water really is everywhere and does so many cool things. What's happening on this page? Yeah, it looks like they're making sculptures out of the water. But what are they using? Looks like chainsaws. Why would they need to use chainsaws to make water sculptures? Because the water is frozen. They're ice sculptures, and frozen water is really, really hard. Wow. Did you like that story? What was your favorite part? Mine, I think, was the deer in the forest drinking from the pond. It just looks so peaceful that I wanted to go there. All right, grown-ups, grab that warm water and that cold water and these supplies for our first set of experiments. Now, while you're doing that, I want to talk a little bit about what we learned from our story. Water was amazing in our story. Like, I learned that water can be beautiful. Do you remember any pages in the book where it talked about water being beautiful? Yeah, you might remember the rainbow, the beautiful colors in the rainbow, or the ice crystals on the window during that really frosty day, or even the ice sculptures at the end of the story. All beautiful water. But I also learned that water is really helpful, and it's helpful to humans and to lots of other animals. Do you remember a page in the story where water was helpful? Maybe you remember the otter getting his food from the water, or maybe even the firefighter putting out the fire with the water, or the bruise shrinker. That's right, we put an ice pack on our bruises to help us to feel better. Water is so helpful. Now, what really makes this story work well is that the author talks about water when it's really, really cold and when it's really, really warm. Now, what happens to water when it gets very, very cold? It freezes. It becomes a solid like ice or snow. Now, what happens if you take that ice or that snow and you warm it up again? It melts. You're totally right. Very good. Water behaves differently if it's really, really warm or really, really cold. So I want to explore this a little bit more. So you can see on my camera here, I've got two glasses, okay? They don't have any water in them right now. We're going to fill up one glass with our cold water, okay? So grab your cold water and take one of your glasses and go ahead and pour your cold water in. I'm going to try not to spill. Now, while you're pouring it, what do you notice? You might notice bubbles. You might notice that your water is nice and clear. Very good. Now, take your hand, and I want you to feel your glass and make some more observations. What do you feel? Yeah, it's cold. That's probably what you expected, right? So hold your hand there for just a second, and then move your hand. Now look at your glass. Do you notice anything? You probably see a handprint there. Awesome job. Very good observation. If your glass was cold enough and your hand was warm enough, you might have left an outline of your hand on the outside of the glass. Excellent observation. Now, let's pour our warm water, okay? So we're going to pour our warm water into the other glass, and we're going to make some more observations. Are you ready? I'm going to try not to spill again. Here we go. I'm going to pour it in. Oh, I see more bubbles, but I see something else happening. Is this happening with your glass too? What do you notice at the top of my glass, my warm water glass? It looks all foggy. foggy. It does look foggy. That's steam. So when water gets really, really warm, not only does it melt and become liquid again if it was a frozen solid, but it can also become steam, which is a gas or water vapor. So cool. Now, it's going to be hard for me to tell these two glasses apart because basically they look the same, okay? They both look like glasses of water. Now, I'm going to add color. I'm going to add red to my hot water or my warm water, and I'm going to add blue to my cold water, but you can add whatever colors you want. I just think red and blue is going to help me keep them straight a little bit better. So I'm going to try to add 3 drops of color to both of them at the same time. Okay, do you think you can do that too? Pick 2 colors of your food coloring and you're gonna add them to your glasses at the same time and we're gonna watch. Okay, so let's look nice and close at our glasses here while I add the color. Okay, are you ready? We're gonna do it on the count of 3. Okay, here we go. Ready? 1, 2, 3. 3 drops. Whoa. Do you notice any difference between our warm water with the red food coloring and our cold water with the blue food coloring? Does yours look this way? What do you notice? What's different about how the food coloring is moving through the water? Yeah, on the red side, it looks like somebody mixed it. There's food coloring all throughout the water. And what's going on our blue side here? Let me kind of clear off some of the frostiness of our glass there. What do you notice? It is slowly sinking to the bottom. It's not filling up the whole glass. The whole glass isn't blue the same way that the red glass is. Wonder why that is. Do you have a guess about why that might be? Well, it has something to do with the tiny pieces of water we call molecules. Okay, when the molecules in water get really warm, they start to move really fast. So let's pretend that we're warm molecules in the water. Okay, so we're going to do a little fast dance. Okay, ready? Be a warm molecule. Moving real fast. Very good. Now, what do you think happens when those same water molecules get really, really cold? They start moving slowly. So do a little slow dance. Excellent. Now be a hot water molecule. Now be a cold one. Now be a cold one. Did I trick you? All right, be a hot one. Very good. So when those hot water molecules are moving really fast, they take the dye with it. So the dye moves really quickly through the water. But those slow moving cold molecules don't move the dye through it so quickly. And that's why it looks so different when we've added the dye. So cool. So we've already mixed up our warm and our cold water. So now it's time to grab that bowl or tray or dish and bring it out. Okay, so we now know about those fast-moving warm water molecules and those slow-moving cold water molecules. But what happens when they meet? That's what we're going to explore right now. So I've got my tray here under my camera, and I'm going to add my cold water to the tray. So find your cold water. Remember, mine is blue. Yours might be a different color. And we're going to cover the bottom of the tray or the dish or the bowl with our cold water. So I'm going to pour in my cold water. There it goes. Looks beautiful when it pours into the glass like that. There we go. So we've got our cold blue water. So grab your warm water and add a little bit of extra dye to it. We want that one to be really dark so we can see what happens when those two colors meet. Okay, so remember mine's red. So I'm going to be adding red warm water to my cold water. What do you think is going to happen when those two liquids, the warm water and the cold water, meet? I predict that it will just all turn purple because when you add blue and red together, you get purple, right? So I predict it's going to turn purple right away. What do you think? All right, let's find out. So we're going to add just a little bit of our warm water to our cold water. Okay, here we go. What happened? Let's look at it more closely. What do you see happening? Does yours look like this? Does it remind you of anything? To me, it reminds me of ocean currents. And that's exactly what we're looking at. We're looking at currents where the warm water and the cold water sort of push against each other. And you can see they're not really mixing yet. We still see bands of warm water sweeping by bands of cold water. It's like a current. What does yours look like? That's so cool. Now, we've learned a lot about warm and cold water. We've seen that the warm water, the dye went through it very quickly because those molecules are moving fast. And we learned that the dye goes through cold water really slowly because those molecules move really slowly. And we saw currents that occur when you have warm water and cold water and they meet against each other and they sort of swirl and ribbon around. I want to show you one more really cool warm water and cold water experiment. And we'll talk a little bit about why this happens. All right, here we go. So here I have a bowl with room temperature water. So this water is not too hot and not too cold, okay? And you can see I got these glasses in there. They're not really important for the experiments, just so I can show you what's going on. So I've got this jar right here, and it's got cold water in it. See, it's colored blue, just like our other cold water. It's even got a little snowflake on the top, so that way we know it's the cold water. And then we got this container of hot water. Now it's colored red, and it's got this cool guy in sunglasses on it because it's hot. Okay, so we're gonna put both of these jars into our room temperature water. They have holes in them, so the water's going to escape. Where do you think the warm water is gonna go, and where do you think the cold water is gonna go? Well, let's find out. So I'm going to put them in, I'm covering up the holes, and then I release the holes, and the water starts coming out. What do you notice about where the water is going? Right, we see our cold blue water, and it's sinking right to the bottom of the bowl. And where's our red hot water going? It's floating to the top. I wonder if I move the position here. I'm going to move the position of my cold water and, oh, nope, it still goes down to the bottom and the red water is still going to the top. So the hot water floats and the cold water sinks to the bottom. Very interesting. Now, what happens if I turn them upside down? What do you notice? Yep, that cold water is still sinking, and the red water is just sort of sticking to the top of the jar because it wants to float to the top. Still doing the same thing. Now, what happens if I flip them over again? So I'm going to flip them this way. Oh, so there's bubbles coming out because in my jars there is a little bit of air. So we got to get all that air out first. So let's shake out all those bubbles. Oh, the bubbles are coming out, and now all the air is out, and there goes the red dye. So where's the red dye going? Yep, the warm water's still floating to the top, and it looks like our cold water wants to sink to the bottom. So cool. So we've learned that warm water floats and cold water sinks in room temperature water. Very interesting. I want to explore floating and sinking. So why don't you go ahead and grab these supplies, and we're going to do some more floating and sinking. Now, grown-ups, you don't need all of the things to try out or to experiment with right now. Really what you need is the bowl of water and aluminum foil. So those are the things you need right now. So go ahead and grab those. So while you're gathering these supplies, I want to talk a little bit about the science of sinking and floating because it's complicated. There are lots of reasons why an object might sink to the bottom of the water or stay floating at the top. And one of those reasons has to do with those molecules. Remember those molecules, the really fast moving ones and the slow moving ones in our water? Well, other objects have molecules too. And sometimes those molecules are really close together. And when they're really close together, that object is usually pretty dense. And sometimes those molecules will be farther apart, and those objects are less dense. So if an object's molecules are really, really close together, and they're much closer than the molecules in the water, it'll probably sink to the bottom. But if an object has molecules that are very far apart, much farther apart than the water, it'll float on the top because it's less dense. But that's only one reason why an object may sink or float. There's lots of other reasons, which is why I want you to explore. I want you to figure out which objects in your house sink and float. But before you start doing that, I want to show you something. So we've got that tin foil, right? Can you find your tin foil too? Now I've cut my tin foil into two pretty close shape and size pieces of foil. So I've got squares here, and I'd like you to do the same. Try to get them around the same size and shape. So I'm going to take my first square of tin foil here, and I'm going to put it in my water. Do you think it's going to sink to the bottom or float on top? I think it's going to float because it feels pretty light, and I think it's going to float on top of the water. Okay, so here's what I'm going to do. I'm going to put it in my water, and we're going to see. Yeah, it's floating there. Is yours floating? Fantastic. What do you think will happen if I push down on the foil? Do you think it'll sink to the bottom and stay there, or do you think it'll float back to the top? All right, let's find out. Here we go. I'm going to push it down. You push yours down too. Here we go. What did yours do? Mine stayed at the bottom. It's not floating anymore. Huh. Well, as it turns out, aluminum foil is more dense. Those molecules are really close together, or closer together than the water's molecules, so it should sink to the bottom. But why did it stay on the top? Have you heard of an animal called a water strider? It's a really cool bug that can actually walk on the top of water. And the reason it can do that is because of something really cool called surface tension. Water molecules like each other a lot. And so at the top of water, they sort of stick together. And if things are less dense and light enough, they'll sort of just sit on top of that tension surface. Now, after this webinar, you'll get access to a blog post that has another really cool experiment to look closer at surface tension, okay? So once we sort of broke through that surface tension there, and our aluminum foil was pushed underneath there, it sunk because it's more dense. Now, let's take this other piece. Okay, it's got the same density as our first piece. So the molecules are the same distance apart. They're still pretty close together. So I want you to take that foil and I want you to crumple it up. Make it into a little foil ball. Okay, what do you think is going to happen with this foil ball? Do you think it's going to float or it's going to sink when we put it in the water? Let's find out. So here we go. I'm going to put it on top and it floats. Okay, just like our other piece of foil did, it floats. So what do you think is going to happen if we push it down to the bottom? Do you think it's going to stay at the bottom or do you think it's going to float back up? All right, let's find out. Here we go. I'm going to push it under. You push yours under too. And let go. What does yours do? Mine floated right back to the top. Oh my goodness. Now, what happens if we take the piece of foil that's underneath the water already, the one that's at the bottom of our bowl, and we crumple it up without bringing it out of the water, okay? So we're gonna do that. What do you think is gonna happen? Think it's gonna stay floating? I mean, stay sunken at the bottom, or do you think it's gonna float? Okay, let's find out. Here we go. I'm gonna crumple it up underneath the water without bringing it up. Here we go. It stayed at the bottom. Did yours stay at the bottom? Huh. So whether or not an object's density or how close its molecules are, it's not the only thing that will keep it from sinking or floating. Because this ball, the one that's at the top, has something the other ball doesn't. It's got air trapped inside of it. When we crumpled it up, we sealed air in there. And that air is a lot less dense than our water. So that air keeps our foil ball floating at the top. So there's lots of things. There's surface tension, there's air, there's density. But really what I want you to do as a family is I want you to figure out what sinks and floats and then try to guess why. Why do some things float and other things don't? Very cool. And as always, as you're doing your experiments, share them with us. We would love to see what your family is up to. Thank you so much for hanging out with me today. Join me next week for our last Kitchen Science webinar. Have fun, learn together, laugh, and I'll see you next week.